You'll note that we're attacking quantum mechanics much faster this time than you would have done it last time, but I'd like to make some strong comments about the wave function and continuous indices. What is a wave function? Well, a wave function, if I write my state, and my state happens to be in a Hilbert space where it has some continuous index as its basis, then I have to write my state as an integral, an arbitrary superposition of those things. What's a wave function? These coefficients. So I think we have a tendency to ascribe wave functions to quantum states. Wave functions only really are appropriate for quantum states when we're talking about a continuous index, and then they're just no more important or no less important than the coefficients of the state in that basis. I'd like to make a remark about the dimensionality of continuous indices. You'll note that if we'd in fact written this in a different basis, that we would have come up with something like that, and there'd be some relationship between these coefficients and these coefficients. But this is also a perfectly valid basis. We can have, even for position wave functions, we can have a discrete basis, like the basis of eigenstates of the harmonic oscillator, for example, Hermite polynomials times Gaussians, or we could use the Fourier basis. Well, actually the Fourier basis would be another continuous one, but we could use the eigenstates of any bound potential, and that would always give us a full, complete basis. The units of these coefficients here, and the units of those coefficients, hold some small surprises. We know that if this thing is normalized, that we have this condition. And we know that if this is normalized, we have this condition. And this is 1. This is not 1 meter, this is the number 1 in both cases. And so we know that this has no units. That, in fact, has no units. We know that has no units because if we have the inner product between two of them, so that has the units squared, and that is a Kronecker delta function, which is either 0 or 1, the numbers. And so this has units, so no units, no units, no units, clear. This is different. Here, the integral actually contains units. So if this is a position, then this has units length, which means together these two have to have units of inverse length. So the c and the x together. Now that could have been divvied up anyway, but in fact, this has already sort of made that decision for us. If this here is units length, so if this is length, then this here must be length to the minus 1, in which case the units of c must be 1 on square root length. And therefore, the units of these states themselves must be 1 on square root length. And we can see that that squares with our understanding of the equivalent relationship for the orthonormality. If I have x and y, we couldn't have ever had this equal to a Kronecker delta because this thing has units together of 1 on length, and this thing does not. However, the Dirac delta does in fact have the correct units of 1 on length. So this has units of 1 on length, which is why when you take the integral of it, you get 1 rather than, say, some number of meters. And now finally we can look at how we can, say, prove this from here. If I were to have this set of states, if I were to find them, so my set J, the state J is going to be able to be described in another basis. And if I describe it by the coefficients uj, so in our old language we might be calling that the wave function of that state. So this is a set of wave functions, that's the set of states, and this is the transformation between them. Then we can show that the inner product between I and j, we just expand out both sides. Don't forget to take the Hermitian conjugate. And do not forget to change your dummy index. This integral is just a dummy index. And now if we use the fact that this inner product here is the Dirac delta, then we can get rid of one of these integrals and we're left with the other one. And you may know from the fact that these wave functions have to be orthonormal that that is in fact the Kronecker delta. There you go. So wave functions are just the coefficients in a basis that has a continuous index. And when you have a continuous index, watch out for the dimensions of your properties. So your coefficients suddenly have dimensions and your states suddenly have dimensions of the inverse square root of whatever the dimensions of that index is.